Okay, it's 40 according to my phone. So, welcome to the second talk of this morning session. Our next speaker is Professor Baohua Fu from Chinese Academy of Sciences, and is going to talk about symplectic singularities arising from cotangent bundles for the next hour. Please welcome.
Okay. Okay. Thank you for the presentation, and also I would like to thank the organizers, the scientific committee, for inviting me to give a talk here. And this is a wonderful place, and also a very nice occasion for meeting people. Many people that I know only from their papers. I know all the names from printed ones, and now I saw them from real life. So it's really nice opportunity to bring the people legendary to the real life. So I'm going to talk about symplectic singularities and cotangent bundles. This will be a joint work with Genio from my institute. In my whole talk, I will work over the number of complex, the field of complex numbers. So let me just start in by introducing you what are symplectic singularities, and also why we are interested in these singularities. So let me start with this holomorphic symplectic variety, symplectic manifold. So in my talk, everything will be holomorphic. So I will I will not write holomorphic every time. So this is just a complex manifold with some symplectic form. So M is a complex manifold. And then omega is just a 2 form. Which satisfies two conditions. First of all, it's D-closed, such that omega is D-closed. And also omega is non-degenerate. So non-degenerate means the top weight form is everywhere non-zero. So wedge is everywhere non-zero. So this would imply, in particular, the canonical bundle of this M is trivial. So this is in a general sense, this is a Calabi-Yau. So let me start with some baby examples. So example one is just the classic one. So if you take just even dimensional vector space, and then you take this omega, just the usual two form. And in particular, this can be easily checked. It's declosed and also non-degenerate. So this gives you a very simple example. In fact, the Bell theorem dark blue. So this is a local picture. So if you are just working in analytic setting, then every symplectic manifold is locally of this form. So there's no local invariance. So we need to find some global ones. So in other way, you can write also this as a d of this sum of xi dyi. So this is just one form. And in this way, you just realize this is the cotangent bundle of just n-dimensional vector space. And in generalizing this, so we can go to a cotangent bundle, the second term. Cotangent bundle, so if you take any x is smooth variety or smooth or just complex manifold. And then you take the cotangent bundle. Of course, on the cotangent bundle, you have a projection to x, say this is just pi. And then on this cotangent bundle, total space of cotangent bundle, it has a one form. It's called a Newell one form. So exists a Newell one form, which is given by, say, if you pick one point. So x and xi means x is just some point in this x, and then xi is in the cotangent bundle and this point. So you just say eta and this point, and some tangent vector, and this point to this total space. Then you just evaluate. Say this belongs to this coordinate space of this x and this point. So you evaluate this and this d pi of this v. So this gives you one form, new one form, and then you can take the derivative. So you take just omega is just a d of eta. So this gives you a holomorphic two form, and this in fact you need to check locally this one form looks like of this form, and then you take the derivative, then you get this this becomes the symplectic form. Symplectic. So in particular, this gives you a symplectic manifold. So this is a baby example. And now I'm going to, these are just a smooth setting. So I'm going to singular setting. So in a singular setting, so we would like to generalize holomorphic symplectic manifolds to symplectic varieties. So this is due to Bourvil. So symplectic variety. This is due to Bourvil. So this is just a normal variety. Normal variety, say W. It's normal and moreover such that it has two conditions. So first of all, you want to the smooth part admits a symplectic structure. So exists a symplectic structure on the regular part. Or two of this W regular. So this is symplectic. So on the smooth part, it has a symplectic structure, and then you need some condition on this structure and for any resolution. So pi from Z to W, any resolution of singularity, and then you can pull back this symplectic form. So this is just defined on the open part, and this extends. So the pullback of this form extends to some global two form on the resolution. And one caution is that this is not necessarily non-degenerate, not necessarily symplectic. So in general, this is not symplectic anymore. But in some cases, it's symplectic. So if moreover, this is the definition of symplectic varieties. So if moreover, this extended to form is again symplectic. Then we call this resolution, we call pi is a symplectic resolution. So this is, in fact, it's easier to say, this is equivalent to say pi is covariant. And also equivalent to say this resolution, this Z is in fact Calabi-Yau, or just the KZ is trivial. So any question? I didn't catch it.
So I can see here you don't require the resolution to be symplectic.
Yes.
So, but if they do are symplectic, does this family have nice properties?
But in general, there's no, in general, if you take a general symplectic variety, there's no symplectic resolution.
So it's not guaranteed they have a
No.
symplectic
I will say some examples.
Thank you.
And also, I need to make one remark. So you say the second condition is quite, it's not so easy to check. For some explicit examples, you can really construct the resolution and check this condition. But in general, it's not so easy to check. So, you found the theorem of Namikawa, which says for the second condition, in fact, it's easy to check to say this is just the equivalent to say W omega is symplectic, symplectic on the rigid part, and W has only rational constant singularity. Rational or constant singularity. So with this theorem, then it's easy to check because the first one is automatic. Usually, in many cases, it's automatic, and then you only need to check the singularity of this variety itself. So it's easier to check. So let me give you some examples of this kind of variety. So the baby example before this is smooth one, and you want to make it singular, so you take a quotient. So C2n quotient by some gamma. So gamma is just a finite subgroup of this symplectic automorphism of this C2n. And then in particular, how to check this is symplectic. So first of all, it has a symplectic form because gamma preserves the symplectic form. So on the smooth part, it has a symplectic form. And then this is smooth. So if you take a smooth variety quotient by finite subgroup, then it's still rational. So you just use the Namikawa theorem. It's rational, and also it's constant because this is this can preserve the symplectic form. So you check this is the symplectic variety in this sense. And also you can also construct a resolution and show any two form extents. So the second kind of example called nilpotent orbit, closure. So you take a nilpotent orbit in some semi-simple Lie algebra. So semi-simple, and then you take the normalization of its closure. So this is the closure, and this is normalization. And then this can be shown by Panshev and Heinig. So they show the normalization becomes the symplectic variety in this sense. So the existence of symplectic form, this is clear, and also we only need to show this singularity is rational singularity, and this can be shown by Panshev and Heinig. And then there are many more examples, like Nakajima quiver variety. Quiver variety. And also, more recently, the lot of studies by physicists and also mathematicians, Coulomb branch. And even in our conference, there's already several talks on this Coulomb branch. For example, by Sampong last week and Arakawa, and also Hanani last week. And also this week we have a talk by Antoine Bourget on this topic, Thursday. So if you are interested in this, then you can go for this talk. And so the last two constructions need to be the representation theoretic and also mathematical physics. And today, the aim of today is try to give some new constructions from geometric way. So today is some geometric construction, using cotangent bundle. So we have seen, so this is a very simple one. You can take the smooth vector space and you take a finite subgroup. So of course you can also take the cotangent bundle and take a quotient by finite subgroup. Then you still get such example. But it's not so interesting. So what I'm going to take is the following. So I take X is smooth variety. And then I consider the algebra of symmetrical tensors. So this is defined just by this global function, global regular function on the cotangent bundle. So this is just a run of regular functions on this cotangent bundle of this X. So this is quite a mysterious algebra, and also this is not necessarily this is not necessarily finitely generated. And then I take the natural finalization map, so a finalization morphism. Just say from phi x, from cotangent bundle of x to the finalization of this one, so spectrum of this C of this Sx. And I just denote this by Zx. Even for any variety, you can always map to its affinization map. So this is just the usual affinization map, because this is just a regular function on this total space. So you have this map. And this is only dominant, not necessarily surjective. And also this one is affine and also normal. So the normality comes from the smoothness of this X. And in my whole talk, I will focus on this morphism. This is really with the natural one morphism. So why this morphism is interesting? Because on the left-hand side, you have this cotangent bundle. So this has symmetric form. And then you would like to carry this symmetric form downstairs. So let me just try go. So let me write again this morphism. I'm interested in the following three questions. So first one is this irrational, one is phi x irrational. If this is birational, then symmetric form on this one carries on to a symmetric form on this one. So this is what I'm interested in. So if this has symmetric form, then you may ask the second question is whether so one is this Zx symplectic. So symplectic in sense of Beauvais. So once you have a symmetric form on the smooth part, then you may ask whether it has a symmetric, it has the only symmetric singularity. And then third one is related to this symmetric form. So one is phi x itself a symmetric resolution. So these are just very three questions which is really fundamental to this simple morphism. So this is the goal of my talk. Try to answer these three questions. There's no time. Oh, okay, I see. So let me start the trivial case. So trivial case. What's a trivial case? Anyone has a? Yeah. Okay, I cannot say this. Yeah. Yeah. The trivial case is x is phi. So why this is trivial? Anyone say? Oh yeah, because in this case, if x is a phi, so this cotangent bundle is also a phi. then the affinization would be just isomorphism, just the identity. So this affine implies this cotangent bundle is affine. And this map is just an affinization map. So everything, if it's itself is already affine, so it's just a map to itself. So it's then this would imply this phi x is just identity. And so in particular, all three questions have a trivial answer. So all are okay, because this is just the trivial one. So it's just an identity map. So this will become smooth. Just the cotangent bundle of this one, and then it's automatically symplectic, and also phi is a symplectic resolution. So trivially. So this is not interesting. And then what's the interesting case? So there are two cases we are considered. So case one. So let me say X is smooth projective. So this is the first case. And of course, this is non-trivial anymore. Because you say, if this X is smooth projective, so you have this zero section will be mapped to zero, mapped to just 1 point, because this is projective. This is affine, so every projective subvariety will be mapped to 1 point. So this will be no more trivial. So phi x will be no more trivial. Is no more trivial. And I need to avoid this trivial case. Because in many cases this is mapped to just 1 point. And in this case, they are studied by Baohua and Jianliu. In fact, in the paper, they show in many cases, like a color biao, and also general type. This map is trivial, is constant. So which means there's no non-trivial global functions on this cotangent bundle. So in many cases, and only interesting case is final case. In fact, so let me give you one example where this is non-trivial. So this is also motivating example. If you take X is a cotangent bundle or is just a rational homogeneous space. You may think of Grossmanian and also even project space and so on. And then you take the cotangent bundle, you have this moment map. This is a moment map, mu to some. In fact, the closure will be some nidpotent orbit closure inside this. So this is a moment map. And it's well known by Richardson. This is nidpotent orbit closure. So this is nidpotent. Nidpotent orbit closure. This is by Richardson. And also this map is only geometrically finite. So this is geometrically finite. Which means if you take a zero point or just 1 point on the open orbit, the fiber is just only finite many points. And then what you can do is try to take this time factorization. So this OP, let me denote by hat. So this is time factorization. So time factorization. And in particular, this would imply this is finite map. And this is birational with connected fiber. Birational with connected fiber. And then this is simply because this is a symplectic, so this would imply this is in fact is a symplectic resolution. So this say mu hat. This is a symplectic resolution. Symplectic of the resolution. Because this is birational and also this is this is color BL, so so downstairs this becomes a symplectic resolution. And now in this case, because this is birational with connected fiber, so you have this mu push forward of this yeah, it's not a good notion, good notation because this all is a structure shift. This is just all downstairs, OP hat. Yeah, this is structure shift. Maybe I change the color. This means structure shift, and this is means orbit. And this would imply the space of regular functions on this coordinate bundle is just regular functions downstairs. Downstairs just OP hat. And then in particular, this would imply just the map the phi x, so phi g mod p, from coordinate bundle of g mod p go to this z of g mod p. So this is just this morphism, this mu hat, this mu hat. And then this imply this is a symplectic resolution. So this gives you a first example where this phi x is birational and zx is symplectic and also phi x is symplectic resolution. So all three questions have a positive answer in this example. And now to answer the third question, so you find this is a conjecture which says if phi x, if x is smooth projective and phi x is a symplectic resolution, is a symplectic resolution, then x must be rational homogeneous. And also phi x is just a mu x. Phi x is just a mu hat. This mu hat, this one. So this conjecture would really answer the third question perfectly if we can resolve this conjecture. And in fact, this is not new. This is just a reformulation of a Form's conjecture. So this is just a reformulation by us, reformulation of Campana Petanet conjecture. Campana Petanet conjecture. So I will not state this conjecture, but in fact, these two conjectures are more or less the same. So this gives a complete answer to question 3, and then I can give our answer to question 1 and question 2. So this is our main theorem last year. Uh, 24. We say first of all, this phi x is birational, so of course x is smooth projective. As before, phi x is birational if and only if this tangent bundle is big. Yeah, I didn't define what the bigness means. This means morally means it has many sections, but it's more tricky to define this. So just escape this notion. And then secondly, in this case, if phi x is birational, then on this zx we have a symplectic form on the smooth part. Then this zx is a symplectic variety if and only if this the projectivization of the tangent bundle is of final type. Is of final type. Final type means it looks like a final variety, but up to ending something. Yeah. So exists some effective Q divisor effective Q divisor such that it has two conditions. First of all, it looks like final. So the final means this minus canonic bundle is ample, but final type means you need to add this extra divisor to make this ample. And moreover, this singularity is not bad. So the singularity is of KLT. And this is our main theorem. So this give an answer, yeah, in terms of birational geometry to these two questions. So in the case of smooth projective, then these three questions have more or less a clear answer up to this conjecture. And then in this paper, we also described many new examples using these two theorems. For example, if we take X is smooth projective toric, then we get this ZX is symplectic. So this in fact this becomes to this in fact is hypertoric. And then we have more examples like if X is a Horosberg with small boundary. Small boundary means the boundary has coordinate at least 2. And then again we have this ZX is symplectic. And so on. So we get really some nice examples in this case. So this is case A. So let me go to case B. So for smooth project case, so we have more or less a complete answer to these three questions. And now for case B, so what would you like to put as case B? Yeah, question. Yeah. You mean this is hypertoric? Yeah. Yeah. This is a question we would like to answer, but we don't know. Not every hypertoric is of this form. Yes.
I see. Okay.
Yeah, this is I think it's a nice question to determine which kind of hypertorical varieties come from this construction. Yeah, yeah, it's a good question. So what would you like to put as a case B? So of course, yeah, we will have studied this smooth projective case. So we'll find something non-smooth projective or non-projective. So the most interesting case is case B is X is smooth quasi-affine, but not affine. Because affine case is already trivial. So this is our second case, smooth quasi-affine. Yeah, I think this is quite not so common for uneven geometry to deal with quasi-affine varieties. Usually we deal with affine varieties or projective ones. But in this case, this is a very interesting case because why? Because if X is a smooth quasi-affine, quasi-affine means it's an open subset of some affine variety. So itself has many global functions. And remember, our morphism, this is affinization. So we need to find a global function on this cotangent bundle. So if this is quasi-affine, then it has many global functions. So this is why this case would be very interesting. So then this phi x from cotangent bundle of x to this zx, in fact, is an open embedding. Is an open embedding. So in this case, question 1 is trivial. So question 1 is trivial. Is trivial. Yeah, because you have always an open subset. This is already just an open embedding. So this is very nice. So you don't need to answer question 1. And then what can we do for question 2? So question 2, in fact, yeah, in your paper of this year, we tell it's in fact in this case. So this is an open embedding, so I can just write this as just the affinization of this one. Is really this Zx really contains cotangent bundle as an open subset. So I just write a bar, and then in this case, X a smooth quasi-affine. Then cotangent bundle of X, this bar is symplectic. If and only if there are two conditions. So first of all, this Sx, remember Sx is just the regular functions on this cotangent bundle. This is finitely generated. Why we need this? Because we would like to have some variety. So if it's a variety, so we need this is finitely generated. And then secondly, it has a symplectic singularities, or just this cotangent bundle has only a rational Goffenstein singularity. Why we need this condition? Because on the first condition, this will give you symplectic structure on this part, on this one. And then by the Lamy-Covered criteria, so to make this symplectic, you only need to check this singularity of this closure. So it's an only rational Goffenstein singularity. So this is a quite trivial observation. But for both cases, it's not so easy to check. For example, first one and second one, the two conditions are not so easy to check. So this is why we're restricted to some special cases of quasi-affine variety. So the first case is called a basic affine space. Basic affine space by Bernstein, Gelfand and Gelfand. In fact, this space is not affine. Yeah, it's quasi-affine, but it's called the basic affine space. This is very important in representation theory. And what's this? So you take any reductive subgroup on reductive group. So this is reductive. And then you take the Baohua subgroup. And then you consider this GMO BB. So this is called a basic affine space. And this is only quasi-affine, smooth quasi-affine. So just a baby example. So you may take a B. It looks like a upstream triangular matrices like this. And then this BB is just like a 1, 1, and then this is 0, 0, something like this. Yeah. This is BB, and then you take this quotient G mod B. This is smooth quasi-affine. And then in this case, in fact, why we are interested in this? You found there's a conjecture by Ginsburg, and Katzan. Katzan conjecture. You find the conjecture, if you take this basic affine space, you take the coordinate bundle, take the closure or the affinization, so this will come with symplectic singularity. This is symplectic. So this is their conjecture. You know why they proposed this conjecture? Because this space naturally appear in representation theory, and then they believe this is something varieties. So baby example, just to give you one example. For example, if you take SL2, quotient by this U, this is BB. In fact, this is just C2 minus 1 point. In fact, SL2 it acts. In fact, SL2 it acts it can permute this C2 to any vector. You can transpose. You can use this axis, left axis, to transpose to another non-zero vector. So this is transitive, and then the quotient stabilizer is just this BB, and then this is why this is asymptotic to this C2 minus 1 point. And then this would imply the coordinate bound of this SL2 mod BB. So this is the coordinate bound of this one, C2 minus 1 point. And what's missing is just this point. So if you take the closure or the affinization, this is just becomes to coordinate bound of C2. Of course, this is symplectic. So this is just a baby example. And for this conjugation, in fact, this has been proven. In fact, known result. First of all, Ginsburg and Hirsch, Simon Hirsch. In fact, they have shown the experiment before. So to show this is symplectic, so you have two conditions. So first one, you need to show this is finitely generated. Second one, this has only rational constant singularity. And the first part can be shown by Ginsburg and Hirsch. So they show this S. This is finitely generated. So they finished the first part. And then secondly, is Jia Bomi. And he showed this conjecture for type A. And then finally, this can be shown by Gardon. Show conjecture okay for all type. So this conjecture has been proven. And but the method of proof is using quite a representation theoretic method. So what's our second main theorem is as follows. So we use some geometric method to give a new proof for this theorem. In fact, we prove something more. So if G is reductive, and this P is parabolic, then we show first of all this S of G more PP is a commutator of this P. So we generalize this B to any parabolic subgroup. So Borel is just one, but there are many parabolic subgroups. So this is finitely generated. And secondly, so this will give you a new proof for the theorem of Ginsburg and Hirsch. And then secondly, the coordinate bundle, the closure of this one, finalization of this one is symplectic. Okay. So this is the second main theorem. And after this one, then you may wonder why we consider this PP. In fact, this is called this space has also a name. This is called Braverman cuts-down space. Just like the affine, basic affine space. So this is similar to for this one. And now try to generalize this one. So you may wonder. Remark is in fact is BB. In fact, it's also the unipotent part. Is the uniradical is the unipotent radical radical of U of B. And then so you may wonder why we consider it was BB, but yeah. But why we try to generalize this also generalize to this G more UB or G more UP. So this is very natural, because you can consider either this one as a commutator of B or just the important radical of this Fourier subgroup. So for the first generation we have already this theorem. For the second one is like this. In fact, this is in this case coordinate bundle of this G more UP. This is called a partial hyperkähler implosion. Implosion. I don't remember who gave this name. Maybe Tensor, Kevin, and and Swan, and so I don't know. For this one, in fact, we have another conjecture due to Tensor, Hanani, and Kerwan. In fact, the conjecture, in fact, this one, this is also symplectic. Symplectic for any p parabolic. So this would give another direction of generalization of this former conjecture of the Ginsburg and Katz. And moreover, in fact, there's a more explicit description of this one by Bourget, who is there, and I don't remember. Someone Grunminger, the Hanani, and John. Maybe I missed someone. Tensor. Tensor. Okay. In fact, the conjecture not only simply in fact this is a Coulomb branch. A Coulomb branch. In fact, they explicitly describe what it should be. In classic type. And this has been proven in type A. So recently, Gardon and Webster they proved this for type A. In fact, we are functoriality of Coulomb branch. And now it's time to announce our second result. In fact, we cannot prove these two conjectures, but in fact, we give a reformulation of these two conjectures in terms of birational geometry, in the same spirit of project case. So maybe. This place is okay. Maybe our last theorem. that's the theorem. So theorem of this year. So we construct some new say new vector space. So this is just a vector bundle over G mod B. So this full flank variety. The fiber is a UP dual. UP dual is just the height of UP. So this is inside this G dual. And UP is just a Lie algebra of this UP. So this is just the height of this one. So this becomes a vector bundle, homogeneous vector bundle over G mod P, over G mod B. And then our theorem is this S of this G mod UP is finitely generated if and only if the projectivization of this vector bundle. So this becomes a projective bundle over G mod B. So is Morley James space, Morley James space. Yeah, I didn't explain what's the Morley James space, but it's a usual notion in bidirectional geometry, and also this coordinate bundle of G mod UP. So this is symplectic. If and only if this projectization is of finite type. So this is very similar to what we stated in this case. So it's the right time to stop here.
Thank you, Professor, for this beautiful talk. Any questions? Yeah.
Yeah, thank you for the very nice talk. Do you know what kind of singularities appear in your symplectic varieties for either case A or case B?
Yeah, we have some examples. Yeah, it's a good question. In fact, yeah, there's something quite strange. Yeah, we found. For example, what we can find. Yeah, I didn't talk about it. Just to give you an idea, what we can find is if you take all mean inside this G, even we can realize this as a coordinate bundle of some quasi-affine space as a affine closure of this one. If G is not of type G2, F4, or E8. So this is quite strange to us. Why only these three types we cannot realize all mean as arising from our construction. And of course, by your conjecture, so if you take just this G mod UP, then we cannot find the new examples other than Coulomb branch. Yeah. So this is.
Thank you.
Another question? I have a very basic question because I'm not so familiar with the geometry and I prefer when everything is algebraic. So what happens, for instance, for elliptic curves? What about question 1, 2, and 3 for elliptic curves or abelian varieties or whatever? Oh, it's trivial. Oh, sorry. Oh, okay, okay. Yeah. Okay, okay. Now I understand. Thank you. Another question? Okay, so please applause the speaker again.